calibration of radio interferometer by emission of natural radio sources and satellites. So please.
Yes, thank you. This is a talk mostly prepared by my colleagues, and I just represented. We implementing project called the application of forward scatter radar method for detection of space objects. And one of tasks to realize this project, first of all, we have to calibrate a radio interferometer. And so antennas itself and interferometer, when we're working with LBI, we have to know precisely about baseline and distance between and delay between antennas. And in this case, in the progress of LBI technology, so sufficiently effective methods of instrument calibration were developed, say, like signals from discrete extragalactic radio sources, like quasars, it gives us precisely known coordinates of antennas, and it also already was mentioned about geodetical LBI. So we can achieve around 0.1 arc seconds of position in International Celestial Reference Frame. This is quite good, but they have some also limitations. Knowing this about the geodetic observations, it gives us information about position of antenna in centimeters precision, currently even less even. So we need discrete radio source, we need precisely known source coordinates and high intensity of emission. And here is some problems because to have high intensity emission, we also have large effective area of antenna. So we can work with rather big antennas, like let's say 12, 13 and higher meters to catch low intensity signals from quasars, which are limiting this method to big antennas. Currently, we have fleets of navigational space satellites like GLONASS, GPS, Galileo, Beidou, which can be a source for calibration of interferometer, so satellites and signal from these satellites. They have high power of emitting signal, and even relatively small antennas can use these signals. They are very known orbital parameters, so they can relay of orbits of these satellites and estimate position of this satellite in very, very good numbers, so in centimeters as well. So the wideband emission around 20 megahertz allow to us use LBI procedures for signal processing. So per moment availability of neutral field of vision for interferometer. So there are a lot of satellites, so they're visible all time, and we can choose between satellites. Those with calibration of interferometer requires careful testing. So one of the options for solving this problem is to include a large antenna or in the LBI network, which make it possible to calibrate part of the network parameters on extraterrestrial radio sources using standard radio astronomical techniques, and to refine the calibration techniques on a quasi-noise signals from the satellite fleet. So it would be also interesting to compare the results of measurements by two methods for two types of sources, natural sources and satellites, in order to identify sources of errors, and if in future to access with discrepancy in the position of objects in different coordinate systems. Currently, geodetic network works only with natural sources and no availability to compare or combine both navigational satellites and natural sources. So we try to realize it. Calibration procedures, evaluation of interferometer parameters are performed by measuring of spatial delay. The delay measurement is performed by the maximum correlation function of signals received by two antennas of interferometer. The delay is determined by mutual position of the source and the antenna and depends on baseline coordinates and radio sources coordinates. In this case, we know very precisely radio sources coordinates and satellite position as well. So for measured parameters, so we're looking for delay. For ambiguous detection of a delay, it is necessary to use a signal with a non-monochromatic spectrum. And here become a bit a problem. So if you're looking for natural sources, extragalactic radio sources, it's located for us in infinite distance, so far field of the interferometer. But if you're looking for satellite signals, they are very close and they have to work in their zone of interferometer. So it can't be combined in one correlation on very difficult to use same interferometer. I already asked colleagues, so we are looking how to combine SFXC, for example, for natural sources and satellites, or other interferometers which use satellites to adjust them to natural sources as well. So problem is to make solution and reduce solving to solve these equations for both cases, for natural sources and satellites. In our case, so in last April we have experiment using two antennas. So it's at 52 T16, which in baseline around 800 meters in L range, L band diapason, which cover exactly navigational satellites transmission and able to catch natural sources. So the maximum parameter is delay. Measured parameter is delay in a maximum correlation function, which carries information about the position of observed object. So it's some example of 3C84 measured here. So the accuracy of a delay measurement is inversely proportional sampling rate of recorded signal, and for our case was equals to 31 nanoseconds, and corresponds to accuracy of path length determined about 9 meters. So response of satellite signal, the form of a correlation function, what you can see here, the peak of a pedestal is due to the structure of emitted signal. So here you see satellite emitting signal. So this pedestal determines peak also in correlation function. Satellite navigational satellite, they are limited with band. Usually it's 10 to 30 megahertz. Accordingly, this sample of delay measurement is fixed to 50 to 17 nanoseconds. Yeah, and here we cannot reduce it because it's a limiting factor of a signal itself. So one sample, 50 nanoseconds, correspond to distance over which electromagnetic radiation propagates on 15 meters. So again, our measurements are limited around these values. So it was made a model measured correlation to a specific delay depending on azimuth of satellites observed during 2 days of observation. It can be seen that this dependence is well approximated by sinusoidal function. The presence of a dependence of a delay corresponds on the coordinates is due to errors in specified of calculated projections of a base, so which we are looking for. Those the measurements and processing can be considered valid. However, this discrepancy of corrections for each source over a measurement period of 5 minutes is quite large in some cases. The approximation error is approximately 10 nanoseconds. So we go to 3 meters in linear measure, which is taken as an error in measurement of base projection. The calculated projection of the base, the approximated value of the correction were used. As a result, we assume so RT32 coordinates are quite good known. RT32 in 3 years ago was participated in geodetic observations. As a result, we obtained very precise values of our RT32 focal point measured in even centimeters. So we assume RT32 is known quite well, and we calculate errors of known RT16 based on our observations and got a difference between known and calculated values, and they are quite impressive. So we try to improve our position, not of 10 meters, but reducing to 1 to 8 meters. So as a result, in spite of good evaluations obtained with space satellites, calculations obtained in sources on the same interferometer were not satisfactory. When receiving radiation from weak radio sources, the presence of a lot of interference signals from nearby satellites was revealed, which made it difficult to measure with delay. 34 calibration based on signals from radio sources at the operation frequency of a navigation satellite did not give reliable values. To solve this problem, it is possible to measure radio sources in our frequency range, since the base of instrument is measured from the point of interception of the axis of rotation of antennas. The result of calibration at different frequencies in principle should be the same. The error of different measurements may differ due to the difference in the receiver systems and observation time. So we're working to repeat these observations, but using cryogenic receivers. Again, here in these experiments, we use L-band, which is warm and not very sensitive instruments. And we have to, it's no problem to observe satellites, but when we start observing natural sources, we see only brightest of them, and with presence of very big noise from the same satellites and artificial sources. So next step for our experiment is to repeat observations in 6 gigahertz, for example, using cryogenic receiver, and compare it with satellite signal in L-band. Hopefully it will reduce uncertainty in baseline measurements. And of course, in the next step, try to combine several correlators results and try to adjust SFX correlator to use satellite data, satellite data observed in near field. Yeah, thank you. So.
Thank you, Vladislav. So do we have questions from audience? At the moment, it looks like not. So you mentioned some ways to improve and make further tests and so develop the method further. Starting with going up to 6 gigahertz with a cooled receiver. So this frequency, is it decided upon only because we do have cryogenic receivers at this frequency, or that there is some other reasoning behind this regarding some available satellites in visible orbits or something like that? Or maybe the method would be even better if we use even higher frequencies.
In this case, maybe I make a correction. So we will use L-band for satellites. So because in high frequencies, no geodetic satellites. So we need satellites with exactly known positions. But using cryogenic receiver, we will observe natural sources like quasars, and they have a broad spectra. So we are not limited in exactly L-band. So we can observe in 4.5 up to 8.8 gigahertz in any frequency with which are free from interference, and try to combine results from L-band observed with satellites.
So the idea is that the method would be as accurate as it is with the satellites, also with natural sources, if the signal levels could be good enough. Do I get it correctly?
Hopefully. So my main idea to combine results from natural sources and the results obtained from satellites and check one and another and make a link between two reference systems.
Maybe in few words, you could sketch in what's the missing information that one or the other system could provide if the method is basically the same. Is it the more wideband nature of natural sources, or that there's some other aspect?
I would say so. If we are using natural sources, so we are limited with antenna size. If we are using satellites, so we can apply this method for even very small antennas.
And since we have a few minutes more for questions, maybe if there are some questions from audience, please interrupt me. If not, I will continue discussion. So you mentioned that the geostationary satellites are used due to their known location, but as we know, they slightly drift anyway. So is this somehow compensated in this method, or it's negligible differences in their position?
No. So you're missing. This is not geostationary. This is navigational satellites. So like GPS and GLONASS, and these constellations of satellites, orbits of these satellites are very good known and corrected in different methods. So itself with optical means, with ground-based stations like we have in Urbane. And we hope we can relay to this data, but not for 100%. Here is also some tricks. So orbits of, for example, GPS may be artificially changed or shifted in some time or some cases. And nobody knows about it except BI antennas. So we have independent measure of precision of satellites in this case.
Okay, regarding the GPS constellations and similar satellites, I do understand now. However, have you looked into also the new sort of mega constellations coming up, like the Starlink and similar, even though they don't provide such accurate data as GPS satellites? Maybe SpaceX or similar companies keep very high precision data on their orbits as well, taking into account how many there are and the coverages they need to raise.
Yes, you are right. I understand your question. So in this case, we can be a provider of precise information of orbit parameters for like constellations, like you say, like so small CubeSats or communication satellites, which are not geodetic satellites, but we can link these satellites, these orbits of these satellites, and to our reference frame, and provide exact positions and orbits of these satellites for them.
Okay, thank you. So if there is some question in the audience, we have still 1 minute for it. Please go ahead. If not, then I will say thank you to Mr. Vladislavs Bezrukovs